Jai Hind to all of you. I am Dr. Ritish Kumar and going to present the lecture on the topic of PN Junction Diode and reverse breakdowns, which lies in the subject of electronic devices, and the subject code is BEC301. In this lecture, we will learn about the different kind of breakdowns happens in the PN junction diode. First, we will start with the syllabus. So this is a university syllabus, as you can see here. So the syllabus is divided into 5 units, and this topic is like unit number 3, as you can see, PN junction characteristics. So I will cover the topic PN junction diode or PN junction characteristics, and also the breakdowns, different kind of breakdowns, the avalanche breakdown and Zener breakdown. These are the books, and I will prefer the first 2 books for the current topics which I am going to deliver the lecture. Before starting the topic of PN junction diode, first we need to understand the Fermi level distribution or Fermi diode distribution in a intrinsic carrier, intrinsic semiconductor, and extrinsic semiconductor, also called a impure semiconductor. So there are two kinds of semiconductor we have. The first one is P-type semiconductor, and second one is the N-type semiconductor. So depending on the doping, we can categorize this. If we do the doping in trivalent, then we have then we have a P-type semiconductor. If we do the pentavalent doping, then we have a N-type semiconductor. So this is a energy band diagram of different kind of semiconductor. The first one is the intrinsic semiconductor, as you can see here. This is intrinsic, N-type and P-type. Basically here we define the Fermi level. So you can see this is a valence band energy level, conduction band energy level, and the mid one is the Fermi energy level. So in the case of intrinsic semiconductor, Fermi level lies just mid of the energy band gap. This is called as energy band gap, as you can see. Energy gap, also called forbidden band gap as well. So in the intrinsic case, Fermi level lies just mid of the energy band gap. And if you look into the N-type semiconductor, so in the N-type semiconductor, the Fermi level lies just below the conduction band. You can see here, just below the conduction band. This is a Fermi level, right? This is a valence band, conduction band, and Fermi level lies just below the conduction band. And in the case of P-type semiconductor, the Fermi level lies just above the valence band. You can look at here. So this is a valence band energy level, this is a conduction band energy level, and this is a Fermi level. This is a Fermi level. Right. So in N-type semiconductor, Fermi level lies just below the conduction band, and in the P-type semiconductor, Fermi level lies just above the valence band. If you look the Fermi direct distribution, this is a Fermi direct distribution of a different kind of semiconductor, and this is a concentration level diagram. So you can see here that the concentration diagram, in the intrinsic semiconductor, or we can say pure semiconductor, we have the same amount of electrons and same amount of holes. In other words, we can say that we have a same carrier concentration for the electrons and for the holes for the intrinsic carrier concentration. And while in the case of N-type semiconductor, you can observe here the concentration density of the concentration is high in the conduction band, while the density of the holes is very low in the valence band. So you can say that the concentration higher, the electron concentration is higher, electron concentration is higher than the hole concentration here. While in the case of p-type semiconductor, we have the hole concentration is higher, hole concentration is higher than electron concentration, right? So this is one we can say, right? So why we need to understand this kind of energy level diagram? Because to understand the PN junction diode and to understand the energy band diagram of PN junction diode, first we need to understand the basic energy level diagram for the different kind of semiconductors. So let's begin with the topic of PN junction diode. So as you can see, this is a PN junction. As we can say PN junction because it has two kind of semiconductor. The first one is a P and second one is the N type. So if you look the energy band diagram of P type semiconductor, as you can see here, and in the last slide we have already studied about the energy level diagram. So this is a energy level diagram for P type, and this one is the energy level diagram for N type. So you can see here the blue the dotted blue line is showing the Fermi energy level. So in the P type, the Fermi energy level is lies just above the valence band, while in the case of conduction band, Fermi level lies just below the conduction band, right? So while making the junction of P or N, then because there is a little bit difference in the doping level of P type and N type semiconductor. That's why we have a potential difference in between them. That potential difference is called as contact potential we have. So if I say in the P type semiconductor we have BP potential, and in the N type semiconductor we have BN potential. So contact potential will be V naught is equal to BN minus BP we have. So if you when you make the PN junction, then at the junction point we have a layer is created near about the junction. This layer is known as depletion layer. And why it is creating? Because due to the diffusion phenomena, what is the diffusion phenomena? When diffusion phenomena is a kind of condition when the charge carrier flows from higher concentration to the low concentration. So in a P-type semiconductor, we have the majority carrier are holes, while in the case of N-type semiconductor, the majority carriers are electrons. So in P-type semiconductor, we have higher concentration of holes, while in the N-type of semiconductor, we have higher concentration of electron. So in the diffusion phenomena, the carriers flows from higher concentration to low concentration. So holes are moving from P type to N type, and electrons are moving from N type to P type. So at the junction point, there is a recombination happens in between the holes and electrons. That's why they are recombined and disappear. So only the immobile charge carriers will present near about the junction. So these are the immobile charge carriers. So in other terms, we can say these are the acceptor ions or donor ions. So in the case of N type, we have a donor ions, and in the P type, we have a acceptor ion. That's why this is a negative sign and this is a positive sign. And this layer is known as depletion layer, right? So if you if you give the direction of induced electric field due to the depletion layer, so electric field always directed towards from positive to negative. So direction of electric field will always be the from N to P direction, right? And this is a energy level diagrams for the PN junction diode, and you can see here this is the energy level diagram for PN junction diode at equilibrium condition, right? Then what is the equilibrium condition? Then there is no biasing we have applied across the PN junction diode. So you can see here, while making the PN junction, we have a single Fermi level, or we can say aligned Fermi level in between p-type and n-type semiconductor, and due to the difference in the doping level, we have a contact potential. We have a contact potential we have. So you can see here, this is contact potential level, and this height is also known as the barrier height, right? So this is a aligned Fermi level throughout the PN junction diode we have. So how you can make it the difference? We have a we have a contact potential, or we have a barrier height. So while making the single Fermi level, you need to make it down, right? You need to make it down and you need to make it up. So to maintain the single Fermi level, to maintain the aligned Fermi level, then the structure will become like this way of the energy level diagram. So that's why this QV naught is known as work function as well, or barrier height as well, right? So this diagram is showing the particle flow, direction of the particle flow, and with respect to the current direction. So the first one is showing the hole diffusion. As I said, the hole diffuse from hole move from P to N side, while the electrons move from N to P side. So you can see this is a hole diffusion and this is electron diffusion. Current will always be in the same direction as in the whole moving direction. So this is in the same direction we have, and if you look into the electron diffusion, electron will always be diffused from N to P direction, and that's why the electron move from N to P, and always the current will be in the opposite direction. So the current will always be in the P to N direction, right? You can see here. What is the drift? We have here, drift always be the phenomena when under the influence of electric field. The movement of carriers under the influence of electric field, and due to the presence of electric field, whatever the current will flow will always be known as drift current, or the movement of charge carrier will known as drift of the charge carriers. So hole will drift from N to P, and electron will drift from P to N, and these are the minority charge carrier for P type and N type respectively, right? So as you can see here, the diffusion current and drift current will always be in the opposite direction, right? So these are in the opposite direction. If you, because there is no biasing we have applied here, so the net current will always be 0. So we can say the diffusion current will be cancelled out drift current, right? So this is a PN junction diode. So next we will cover the different kind of biasing of the PN junction diode. So PN junction properties we have. So you can see here, this is PN junction diode. So in the forward bias, what is the forward bias? When you connect P with the positive terminal of the battery and N with the negative terminal of the battery. So this kind of connection of battery is known as forward bias. And in the case of reverse bias, you can see the P is connected to the negative terminal and N is connected to the positive terminal, and this kind of connection of the battery with PN junction diode is known as reverse bias. Right. So these two kind of biasing we have in the case of PN junction diode. So in the PN junction diode, when you connect the P terminal with the positive and N terminal with the negative, and due to the positive connection with the P terminal, the hole will move towards the N direction, N type, and electron will move towards the mean P type. So diffusion current will increase in that case. So you can see here this is a correct IV characteristics of PN junction diode. As you already aware about the PN junction diode characteristics. So this is a forward bias characteristics. We have non-linear characteristics. That's why we call PN junction diode is a non-linear device, right? Non-linear active device, right? Why we call the active device? Because here for the here we need a battery connection to give some result of the PN junction diode. So that's why we call this is active device. So you can see here this is a forward bias characteristics and this is a reverse bias characteristics. So in the forward bias, the current will increase continuously non-linearly if you increase the forward bias voltage. If you increase the reverse bias voltage at a certain voltage, it will become at certain point the current will increase drastically while little change in the voltage, reverse bias voltage. So this kind of phenomena is known as reverse breakdown we have. So there are two kind of breakdown we have. The first one is the Zener breakdown and second one is the Avalanche breakdown that we will study in the further slides, right? So these now I will be covering the topic of space charge region, that is also known as depletion region, right? So here you can see, you can observe here there is no connection of the battery. That's why we call it is a kind of equilibrium states. As in the last slide we have already studied about the equilibrium PN junction energy level diagram. So you can see here this is a contact potential V0. This is a difference in between potential at P side and potential at N side, and this height is known as barrier height. This height is known as barrier height. Also we can say this is contact potential, barrier height, etc., right? So this is a energy level diagram of PN junction diode, as we already studied into the last slide. So here we have aligned Fermi level, and this is a particle flow direction, and this is the current direction we have in the case of PN junction diode. And at because it is at equilibrium condition, so we have a resultant current is 0. So if you talk about the number of current components, we have 4 number of current components. We have the first one due to the holes, and second one is due to the electrons. Due to the holes, we have 2 kind of current, diffusion current and drift current. And while the for the electron case, we have 2 kind of currents, the diffusion current and drift current, right? And if we talk about at the equilibrium condition, the total equivalent current we have is 0, right? Because there is no connection of the battery. The next one is in the case of forward bias case we have, and the effect of forward bias in the over the depletion region. So in the last slide you can see here the field is direct towards the N to P, and if in the forward bias you need to connect P to the positive terminal and N should be connected with the negative terminal, right. So in the forward bias case the depletion layer will be decreased, right. Depletion layer will be decreased, that's why the this barrier height will be reduced by the amount of V naught minus Vf, and Vf is the applied forward bias voltage, right, by the amount of Bf. So as you can see here, this is a reduced contact potential, or we have a reduced potential barrier, uh, right. So this is a work function or reduced barrier height. Why it is happening? Because in the case of forward bias, the electric field is getting mean if you say the direction of the electric field in the due to the depletion region is always in the direction of N to P, while in the case of outer side applied voltage the electric field is in the direction of P to N. The resultant electric field will be reduced due to the applied forward bias voltage. That's why this depletion region is getting reduced. In other terms, we can say uh, because in the forward bias the current will increase continuously, and more number of charge carrier will be migrate from P to N and N to P. That's why this depletion layer will be getting reduced, right. So this is a carrier flow, particle flow, or we can say the majority minority carriers flow direction flow, and this is the current directions we have. So you can see here the intensity of the arrow. Bigger arrow is showing the higher intensity, and lower arrow is showing the lower intensity. So the hole diffusion intensity is higher compared to the hole drift intensity. The direction will be same as we have studied in the last slide. So you can, but the hole diffusion current intensity is higher compared to the hole drift current intensity, while the electron diffusion current intensity is higher compared to the electron drift intensity. So in this forward bias case, we don't have a zero current, zero resultant current. We have a certain kind of current in the forward bias, and it is a kind of non-linear currents, right. So this is a PN junction diode in the reverse in the forward bias region. So we can say for the forward bias region, the depletion layer width W decreases as we increase the forward bias voltage, right. So this is a conclusion of forward biasing, right. The another one is the reverse bias case. In the reverse bias case, the depletion layer increases in the width of the depletion layer increases as you increase the reverse bias, right. So you can observe here, and this barrier height is increased by the amount of BR. This is applied reverse bias voltage. So you can see this is barrier height is increased by the amount of reverse bias voltage. It is happening due to the the intensity of this induced electric field is increased due to the presence of applied voltage, and due to the applied voltage the external electric field direction towards in the same direction. That's why the resultant electric field within the depletion layer will become increased. That's why this depletion layer width will increase, right. So So at last I will conclude the biasing concept over the depletion region. So depletion layer will decrease when you increase the forward bias voltage, and if you increase the reverse bias voltage, then we have a increased we have a increased increase we have a uh, increment in the depletion layer width. Now the next topic is the reverse breakdown in the PN junction diode. So you can see here, reverse breakdown can occur by two mechanisms, each of which requires a critical electric field in the junction. The first one mechanism is called as Zener effect, which is operating at low voltages. The second one breakdown is the avalanche breakdown. So these characteristics we already studied in the last slide. This is a forward bias, reverse breakdown, and we have two kind of reverse breakdown. The first is Zener breakdown, and second one is the reverse breakdown. And at low voltage we have Zener breakdown, and at higher voltage we have avalanche breakdown. So Zener breakdown. So Zener breakdown is when a heavily doped junction is reversed where the energy bands become crossed at relatively low voltages. That's why we have a Zener breakdown, and Zener breakdown is happening due to the tunneling phenomena happening in between the junction. And how it happen? Because it is a heavily doped junction, so this is a simple PN junction diode energy band diagram. Because this is a heavily doped junction, right? So in the heavily doped junction, in the reverse bias case, as we know that the barrier height, this is known as barrier height, is increased by the amount of applied reverse bias voltage, right? So how you can increase the barrier height while down doing the energy level down at the end side. So if you make it down at certain level, this conduction band energy level uh, lies just in front of the balance band energy level of the p side. As you can observe here, when it make it down, then this conduction band energy level of n side will become in front of the energy level of valence band energy level of p side. As we know, the balance band energy level is totally filled energy level, and the conduction band energy level is totally empty level. So because conduction band just lie in front of the valence band, so electron will moving directly towards the p2 end side through the tunneling phenomena. This phenomena is known as tunneling because the electrons directly migrate from p2 and p2n, and in other words we can say the electron of p side valence band is directly moving towards the n side of conduction band. So this phenomena is known as tunneling phenomena due to the direct transfer of electrons from p to n. That's why a kind of breakdowns will happen, and this breakdown is known as Zener breakdown, and this phenomena is known as tunneling phenomena. So in Zener breakdown we have a tunneling effect. So I hope this one is clear. This topic is clear to all of you. The second one is, in other terms, this is second type of energy band diagram, which you can clearly see here, because we are seeing here heavily doped junction. That's why in the heavily doped junction, the Fermi energy level lies within the balance band you can have, right? And the in n side, the Fermi level lies just above the conduction band, right? So this is a heavily doped PN junction diode energy level band diagram, right? So this is again we are saying about the tunneling phenomena, and this is a characteristics of Zener breakdown. Zener breakdown happens before the avalanche breakdown. in the characteristics, because Zener happens at low voltage and avalanche happens at some higher voltage related to the Zener breakdown voltage, right. So we can say the crossing of the bands align the larger number of empty state in the n side junction conduction band opposite the many filled state of p side balance band, right. So this is a Zener effect, we can say. I hope this Zener effect or tunneling effect you can understand. uh, The next one is the avalanche breakdown. So this breakdown happens for the lightly doped junction. Tunneling is negligible, and breakdown mechanism involves the impact ionization, also called as carrier multiplication. Right. So always the electron moving, when you energize the semiconductor, electrons jump from valence band to conduction band, and then at some certain times it loses its energy and recombine again with the holes. So in the PN junction diode, this electrons moving from valence band to conduction band, then the conduction band to the conduction band of the n type semiconductor due to this potential hill, right. What is the carrier multiplication? As you can see here, when this electron moving from p to n side, it will cross the PN junction layer, that is the depletion layer. In depletion layer we have a uh, uh, immobile charge carrier, or we can say ions. When the electrons strikes one ions, it will create ions and one extra electron as well. So uh, just correlate the thing, when this electron strikes uh, ions, then we have a mean ion and the second electrons, and these two electrons when strike to the another one immobile charge carrier, then we have again uh, total number of 4 electrons. So we can say when electron strike with ion, we have a one this electron generate one electron and one ion, right. So this one electron can generate multiple of electrons at the n side. So this phenomena is known as carrier multiplication, and due to the multiplication of the carriers, we have a increment in the current as well, and due to which the breakdown will happen in the case of reverse bias. So we have two kind of breakdowns. First one is Zener breakdown, and second one is the avalanche breakdown. So Zener breakdown, so this is a difference in between the Zener breakdown and avalanche breakdown in terms of doping, in terms of mechanism, in terms of characteristics, temperature coefficient, and breakdown voltage. So in terms of doping, in Zener breakdown we have a higher doping level, and in the avalanche in lightly doped PN junction diode we have characteristics we already we have studied in the lecture. And if you talk about the breakdown voltage, so Zener breakdown happens at some lower voltage, while in the case of avalanche will happen at some certain higher voltage. As you can see here, this will happen at lower 4 volt, lower than the 4 voltage. This will happen at a higher than the 8 volt, right. So in this lecture we have studied about the PN junction diode, then energy band diagram of the PN junction diode, and then study about the effect of different biasing condition over the depletion layer. As we know, as we studied that if you apply the forward bias voltage, the depletion layer width will become decrease, and if you applied the reverse bias voltage, then the depletion layer width will become increased. And in the reverse biasing, we have two kind of breakdown, Zener and Avalanche breakdown. So in this lecture, you already I think you can understand the things. Thank you to all of you.